This time we're going to be looking at the contribution to the frequency response of zeros which are not at 0 Hz. So these are terms which appear in the numerator of the general expression as 1 plus j omega divided by minus z. That sort of term. And when we transform this into the decibel format, so we can add up the effects of the poles and zeros rather than having to multiply them, that would give me 20 log to the power of 10 of the modulus of 1 plus j omega over minus z. And it would be plus because it's on the numerator. If you plot this, it's the gain in dB due to that zero, then you end up with a curve like this. It has limiting forms at both low frequencies and high frequencies, which are quite simple. You'll notice that once again I've plotted decibels on the y-axis and the log of frequency on the x-axis. This time I've moved to hertz rather than radians per second, but that doesn't make much difference. I can express my z, my zero, either in terms of radians per second or hertz, and if I expressed it in terms of hertz, then the omega there would just be replaced by an f. Effectively, I'd be dividing the top and bottom of this by 2 pi. So let's look at those low frequency and high frequency limiting cases. At very low frequencies, we'd have the useful fact that this term here, the j omega over minus z term, is very, very small. So small that we can neglect it in comparison with the 1. So we would just be left with 20 log 10 of 1, and that's 0. In other words, in terms of dBs, this 0 doesn't have any effect for frequencies a long way below the modulus of z. On the other hand, at very high frequencies, where we make the opposite assumption, that j omega is now so big that this term here is going to dominate the 1, and we can neglect the 1 in comparison with this term here, we would end up with 20 log to the base 10 of the modulus of j omega over minus z. Well, the modulus of j omega over minus z is just omega over the modulus of z. And I'm writing it as modulus of z rather than z because in almost all cases that we come across, the z is actually going to be a negative number when we calculate it. Using the useful result that log of a over b is log a minus log b, that just gives me 20 log 10 of omega minus 20 log 10 of the modulus of z. And that is the effect of the 0 in dB. Once again, it's a straight line. Y equals mx plus c. At least it's a straight line, provided I use the logarithm of frequency as my x-axis. And the gradient of the straight line is again going to be 20. So at low frequencies, these zeros have no effect at all. At high frequencies, it causes an increase in the gain at the rate of 20 dBs per decade of frequency. Now, you can extrapolate both the low frequency and the high frequency approximations and end up with something known as the break or the corner frequency. And that occurs where the low frequency approximation and the high frequency approximation give you the same result. In other words, where 20 log 10 of omega minus 20 log 10 of the modulus of the 0 z is equal to 0. That's the high frequency approximation, that's the low frequency approximation. Hopefully it's obvious that this is going to happen when omega is equal to the modulus of z. So that is our break or corner frequency. And once we know that frequency, we can see that a long way below that frequency, the zero has pretty much no effect whatsoever. A long way above that frequency, the zero is increasing the output by 20 dBs per decade. And around that frequency, the zero has an effect, but it's not a sudden one. The output slowly increases from its zero gradient to its 20 dBs per decade gradient. In terms of the phase, we'd have to go back to the expression in this form here. And note that we could write that in a polar form as A, where A is the magnitude of this, times e to the power of j times the arctangent of the imaginary part of this divided by the real part of this, the imaginary part of this being omega over minus z. Now, bearing in mind that z is almost always going to be a negative number, this gives me, for low frequencies, e to the power of j, the arctangent of something very small, in other words, no phase shift at all. And for very high frequencies, omega is going to be much, much bigger than the modulus of z. This is going to be a very large positive number. Again, because z itself is negative, so minus z is positive. So at very high frequencies, this is going to be a large positive number. The arctangent of a large positive number is around about pi over 2 or 90 degrees. So at high frequencies, a long way above the break frequency, the effect of a zero is going to be to introduce a phase shift of around 90 degrees, with the output being ahead in phase of the input. That's the end of this one. Next time, you will not be surprised to learn that the video will be about the effect of poles.